Okay, so let's look at error coding. So error coding is an extremely important area. What we really want to do is to be able to make sure that when we receive bits in error, and there will be bits in error, that we can actually either detect when they're in error or to be able to correct them. Last thing we really need is to be receiving bad data. Okay, so it's part of us looking at data, video, audio, and images. So the first thing that we'll have a look at is what's called modulo 2. So modulo 2 is an important area because much of the operations that we actually do inside our error coding are to do with very simple operations called modulo 2. And modulo 2 is fairly simple and allows us to build really complicated circuits with very simple logic used in it. So they can be very fast and can be quite minimal in terms of the components that we actually use, and also the processing requirements of our devices. And basically, when we have to do our adding together, it's a bit like a binary adder. A 0 and a 0 gives us 0, 0 and a 1 gives us 1, 1 and a 1 gives us 0. Remember when we used to do that at school, that would be 1 and 1 is a 2, which is a carry 1 and a 0. In modulo 2, we ignore any carries and we keep it quite simple. So a 1 and a 1 is a 0, and a 1 add 0 gives us 1. Okay, so these two operations here gives us our binary add, and we would actually define this gate as an exclusive OR, which actually appears quite often in our error coding circuits. Then for takeaway, 0 take away 0 gives us 0, 1 take away 1 gives us 0, 0 take away 1 is 1, and 1 take away 0 is 1. Okay, so again, it's a bit like an exclusive OR. Then when we come to multiplication, it's the same, but in this case 1 times 1 gives us 1 there. This one is equivalent to an AND operation that we would see in our logic. Okay, so the way that we represent our values, if we want to create a calculation or represent them mathematically, is that we typically use this format here. So our first digit is that value, then our second one is x to the power of 1, then we have x to the power of 2, there's no x to the power of 3, and then this is x to the power of 4. So this value here is represented in a mathematical form with that. This one here, we have a 1, and then this is x to the 7. So this becomes x to the 7 plus 1. Okay, there is a value here, and we can see that all the bit patterns, all the bit values are actually set. So we have 1 plus x squared plus x to the 3, and so on. And the advantage with this is that we can actually take a value such as this, 1, 0, 1 times 1, 1, 0, and we can represent it in a mathematical format. So x squared plus 1 multiplied by x squared plus x. So that gives us x to the 4 plus x to the 3 plus x to the 2 plus x. And then if we represent that back in binary again, that's 1, 1, 1, 1, and we have no 1s there, 0. So that becomes that. So let's have a look at this in action. So we'll just pull up our web page. And this is a binary multiplication. So we're writing our little Python program to be able to do that also. But we'll just have a look to see what this looks like in terms of our multiplication. And here we are. Okay, so let's take an example here. 1, 1, 1, and 110. Okay, if you're interested, the decimal values are these, but really we don't multiply in the same way as we would with our integers. So in this case we have x squared plus x plus 1, and we have x squared plus x multiplied together. So in the long-handed way with long multiplication, so we take our 0 and it becomes 0, 0, 0, 0, and now we add a 0 and we multiply 1 times 1, 1 times 1, 1 times 1 gives us that, and then we add 2 zeros and now we multiply by that value, so that gives us that there. Then when we do the calculation, a 0 add 0 add 0 gives us 0, 1 add 1 is a 1, and then 1 add 1 gives us 0, and modulo 2, there's no remember, and then a 1 add a 1 gives us 0, and a 1 add nothing else gives us a 1. Okay, so that's the result of the multiplication modulo 2 of 1, 1, 1 times 1, 1, 0. So there's a Python program that you can try out to be able to get that to work. But we'll try another one here. So let's go for this one. Okay, so there it's there. So this time we've got a 1 here. So we'd multiply the 1 by there. Next time we've got a 0. So we just ignore. And then the next one we add 2 zeros. And there's the value there. And we would go ahead and multiply. Okay, so this is a really fast way to be able to multiply two numbers together to give us our value. Basically, we can implement it with very simple exclusive OR gates. Okay, so that's our binary manipulation. Okay, so what happens if we get two values that are the same? So in this case, we've got 2x to the power of 4s there. Well, actually, that in modulo 2 becomes a 0, or we can ignore it. If we have 3 values like this, and then that goes, and we end up with just x to the power of 4. But x to the power of 4 plus x to the power of 4 will be 0, and we can actually delete it. Same here, 1 and plus 1 gives us a 0 here. So this equation here actually becomes just x squared. Okay, so we can easily change the values using that manipulation. Okay, so here's an example here. So we have 1, 0, 1, 0, 1, 0, 1 times 0, 1, 1, 1, 1, 0. So we represent 1, 0, 1, 0, 1 with a 1, no x, x squared, no x to the 3, and x to the 4, which is this value here. And then we have that. So we have no 1s, we have an x squared, and an x to the power of 3, which is this value here. Now what we do is we multiply the values together. So x to the 4 plus x to the 2 plus 1. And over here, x to the 3 plus x to the 2 plus x. Run out of space. So we multiply that one by that one to give us x to the 7. This one by this one, which is x to the 6. This one by this one, which gives us x to the 5. And so on. So we end up with 9 values here. So the one thing to notice is that we should be able to get rid of the x to the 5 because there are 2 of them, and the x to the 3 because there are 2 of them. So we end up with x to the 7, x6, x to the 4, x to the 2, x to the 1, which gives us this value here. Okay, so we'll just check that with our link here. Okay, so you should find there's lots of different examples on the associated website. So this is 1, 0, 1, 1, 0, 1, 0, 1 times 0, 1, 1, 1, 0. Okay, So this was our x to the 4 plus x to the 2 plus 1, x to the 3, x to the 2 plus x. So here's the working out for that. There's a 0. And then the next one we have a 1. So we add in a 0 to move it along 1. And then there's the value goes in there. Next one is a 1. So we add 2 zeros and then we put our value in. And then the next one we add 3 zeros. And we're multiplying by this one. And we put our value in. The last value is a 0, so we end up with zeros. Okay, so all zeros there gives us 0, a 1 and a 0 and a 0 gives us 1, and so on. Okay, so our result, and hopefully that's the same as what we had before, if you remember. It should be 1, 0, 1, 1, 0, 1, 0, 1, 1, 0. If we go back to our calculation, hopefully 1, 1, 0, 1, 0, 1, 1, 0. That works perfectly. Okay, so that's how we do our binary multiplication, and that's how we can analyze our values. And then another common operation that we have is modulo 2 division. So with division, it's a bit like long division that you would do at school. So we'll just try this one. So 1, 0, 1, 1, 0, 1 divided by 1, 0, 1, 0, 0. Okay, so we go along and that goes into that 1 time. Then we put that there. And then 1 minus 1 is a 1. And then the other two are got to be zeros in there. So we'll just exclude them. So then we bring down this one here. Okay, so we now have a 1 and a 1. That can't divide to that, so we'll bring down the next one, which is a 0 here. That one goes into it this time, so then we'll do that one. Now we'll end up with a 0 and a 1. Excellent. And a dot, just leave that off. And then we'll bring down our 1 here, and then that goes into that once. 100, 100, sorry, not 100, and we end up with a 1. Okay, so this becomes our remainder. This is actually a really important value and shouldn't be ignored. So that divided by that, modulo 2 gives us that, remainder that. Okay, so this is what we would use when we were actually calculating things like an error checksum. So we'll give that one a little try with our website. Okay, so the actual value that we had was 101101 and the result of the remainder should be 1011, which is correct. And hopefully there's a remainder of 1, which is also correct. Okay, so there's the working out for it. So we're taking this value and dividing it by this value. So this was the calculations that we've seen before. So you can use this page in order to be able to show your working out and actually check your results. Okay, so there's the example there. Or there's an example there where we have no remainder, and that becomes actually quite important. So with this one here, if we try this one, we get a remainder of 0. Okay, and when we look at our error checking, this is typically the one that we would actually look for. Okay, so that's modulo 2 division. Another key concept that we have with inside our error detection and error correction is the Hamming distance. So the Hamming distance is the number of bits that need to change between one value and the next. So we can see here that's one change, and then there's another change that would happen between the second bits there, and then there's another one that would happen between the second last bit in this one. Okay, so the Hamming distance is the number of bits that would actually have to change for us to go from this value here towards that value. So we'll check what the answer is rather than calculating it. So in this case, the Hamming distance is 4. 4 bits have to change. I think that's one there, that's one there, and we have another one there, and there's another one here, I think. Here. These 2 bits. These 2 bits, and that bit, and that bit. So it's these 2 bits and these 2 bits that would have to change to take that code into that one. So we define that as the Hamming distance. Okay, so here's a Hamming distance here. Okay, how many bits do we need to change between 111 and 101? Well, we only have to change 1 bit in this case, so that has a Hamming distance of 1. This one here has a Hamming distance of 5. So 5 bits would have to change this bit, this one, and this one would have to change to give us our Hamming distance of 5. Okay, so the Python code is actually there, and we've used 2 ways to actually calculate it, just to make sure. There's a little manual way to actually do it, and then we've also used a library to be able to check our Hamming distance there. Okay, so a Hamming distance is important because if we're going to be detecting our errors and also connecting them, we need to know how many bits might have changed between them. Okay, and we represent it like that. The minimum distance between code 1 and code 2 gives us our Hamming distance. So the rules are, if we want to be able to detect if we want to be able to detect an error in our bits, if we want to be able to detect an error in the bits, then we use this calculation. We use this one here, and the Hamming distance must be greater than or equal to n plus 1, where n is the number of errors that we're trying to detect. And if we want to correct, then it's 2m plus 1, where m is the number of errors that we're trying to detect. So let's look at an example. So in this case, we have our code. So we'll just see what the Hamming distance is between these ones, because in this case we've got 4 codes now. So the 4 codes, then we can see the Hamming distance is 3, and that's the minimum distance between 2 of the values. So in this case, the minimum distance that we can have is between all zeros and 0, 1, 1, 0, 1. And the Hamming distance for this one here is a 1, because it only takes 1 change to go from one of the codes to another one. Okay, so let's say we wanted to be able to detect n errors. So what will the Hamming distance have to be for that to actually happen? Okay, so in this case we have a value of 2 here, so that becomes 3. So the Hamming distance for our codes must be greater than or equal to 3. So in this case, what we need is we need for this a value of 2 to be able to detect 1 or 2 bits in an error in the code. Okay, so if we wanted to detect 2 bits here, we'd have to have a Hamming distance of 3. And when it comes to Hamming correction, we have 2 times the number of errors plus 1. Okay, so with a Hamming distance of 3, we can, with a Hamming distance of 3, we have 2 times 1 plus 1, which gives us our 3, and that's equal to it. Okay, so with a Hamming distance of 3, we can error correct one error. Okay, so in this case, if we have a distance of 3 between our Hamming, then we should be able to match this one to this code here. Okay, so here's an example. So we have our what's the Hamming distance between these codes. So we'll just check that. So the Hamming distance is 4 for them. Okay, so we have a Hamming distance of 4. So d of c is greater than or equal to n plus 1. So if we have a Hamming distance of 4, then we can detect up to 3 bits in error. To be able to correct, our Hamming distance is greater than 2m plus 1. So if we have a Hamming distance of 4 with this code here, we can detect 1. 2 wouldn't work because that would give us 5 here. So we can correct up to 1. We can correct up to 1 bit in error. Okay, so the correction is important because the correction actually knows which bit is actually in error. So in this case, we have a Hamming distance of 4, which gives us the ability to correct 1 bit or to detect 3 bits in error. And then for this one here, we'll have a look to see what the Hamming distance is. So we have a Hamming distance of only 2 now, because these 2 values here only differ in 2 bits. So if we go back to here, and we'll recalculate. Okay, so this is a Hamming distance of 2. So to be able to detect between our codes, so that's 2 greater than n plus 1. So we can see that the value must be 1. So we can only detect 1 bit in error. When it comes to correction, 2m plus 1, then unfortunately the only value that will fit is m equals 0, so we cannot correct that code. We can only detect 1 bit in error. An important area for us to be able to look at in terms of our communications infrastructure is to look for basic probabilities of events actually happening. So I'll have a look at some very basic probability theorem here, but later on we'll look in more depth at this area. So the most simplest form is really where we have an event which is mutually exclusive, such as what's the probability of me throwing a 2 or a 3 if I have a dice. So that probability is mutually exclusive. So I cannot throw a 2 and a 3 at the same time with a single dice. So the probability of me throwing a 2 is a 6, and then the probability of the 3 is a 6. So we end up with the probability of a 2 or a 3 is equal to 1/3. If we have 2 events happening which are not mutually exclusive, then we must take the probability of the event plus the probability of the other event, and then take away the probability of both events happening at the same time. Okay, so that's basic probability theorem. We also have other calculations. So the probability of something, of event X and Y happening, given that we have a probability of X is equal to the probability of Y knowing that that X has occurred. And the same again for X and Y, it's the probability of Y times the probability of X knowing that Y has already occurred. And then finally, the probability if they're mutually exclusive or independent of each other, the probability of X and Y is equal to the probability of X times the probability of Y. So in this case, the probability of us throwing a 2 and a 3, and they're independent from 2 dice, is equal to 1/6 times 1/6, which will give us 1 in 36. The opportunity of us throwing a 2 and a 3, and a 3 and a 2, or for them together, will obviously be twice that. So we end up with an 18th. Okay, so we'll be looking at probability theory in a bit more detail later in the module. So when we look at a communication channel, this is what we might actually see. So we have a 0 here, and what's the probability that we have an error, or that we have no errors and that it's received as a 0? And then what's the probability of an error, so that it's received as a 1? So we typically have an equal chance for a 0 becoming a 1 and a 1 becoming a 0, and that's typically defined as the error probability. Okay, so the probability that it will not change is 1 minus p, and the probability that will change is p. So the probability that we'll have no errors in terms of transmitting n bits is 1 minus p to the power of n. And then the probability that there'll be an error is 1 minus that value. Okay, so that gives us our basic error probability rate. Okay, so if we look at the probability of a single error being transmitted with inside a number of bits is equal to p, 1 minus p to the power of n minus 1, where n is the number of bits. And then if we've got n bit positions, then we end up with the probability of a single error as n times p, and then it's 1 minus p to the power of n minus 1. So it's best illustrated with an example. So if we take 256 bits, and we have a single error probability rate of 0.001, then the probability that there'll be no errors at all will be 1 minus the probability to the power of 256, which is 0.774. And then we can take that away from 1, and we get the probability of a single error. The probability of an error overall. If we just want to calculate the probability of a single error, then we will use this formula here, and we can calculate that as that value. Okay, so that's the overall probability of an error, and this is the probability of a single error with inside our 8 bits transmitted. Another concept that we have in terms of our error coding is what's called linear and cyclic codes. So a linear code is one where we can take two values, and then when we sum them together we get the same code resulting. So if we took a 0 and a 1 and a 1 and a 0, we'll end up with 1. So this is a linear code, and this is another example here. A cyclic code is where we have a linear code and also where we can have a cyclic shift to be able to shift the value and still end up with the same code. So in this case, if we shift this value by one position. That way we end up with 1, 0, 0, sorry, 1, 1, 1, 0, and that code is there. Okay, so is this code cyclic? You can check. So now let's look at some error coding principles. One method that we can actually have is to be able to take the values in a block and then to create a checksum for it, or to create a basic parity. So it's quite simple. So all we have to do is take our values as we have. We'll take 8 values, and then we'll create a very basic modulo 2 checksum for it. So in this case, we've got a 1 and a 1, that's 2 1s, 3, and then we need another 1 to make it 4. So it's 1 plus 1 plus 1 equals 1. Okay, and we're defining this as even parity. So if we add a 1 to the end of that block, then we're making it even parity. So the great thing with this is that we can build this up purely with exclusive OR gates. Great thing is that we can detect single bit errors within a certain column, but we can't detect 2 errors within a single column because the actual checksum bit will be actually correct. We can check and we can know if there's an error inside different columns, but only if it's a 1 bit error. So we'll just have a quick look to see, as an example, to see what this actually looks like. Okay, so this is our block. This is a block code here. So we can see here we're taking these values, and then hopefully when we do our calculation, there's a 1 and a 1 and a 1 gives us 1, and then the next column a 1 and a 1 and a 1 gives us 1. Okay, so it's a bit like our modulo 2. Well, it is a lot like our modulo 2 arithmetic that we actually have. In this next column we have 1 and a 1 and 1 and then another 1. Okay, so we already have, that's in modulo 2, that's equal to 0. So we get that. So if we use even parity for our block code, we get that. And if we want to flip it, we get odd parity, which will just inverse our resulting value there. Okay, so as long as both sides know if we're using odd or even parity, then we can actually check. So these values are sent, and then at the end of the block, this value is sent at the receiver. The receiver will do a quick checksum against it, and then it could take all these values, and if it ends up with 0, all zeros, then there's been no error. Okay, so if this bit was to flip, then when we check the parity, then that would become a 0, and it would match the value that we have here. Okay, so there's a number of examples that you can actually try out to see how it actually works. And this is an example with us taking integer values. So we take integer values and we can work out what the binary patterns are, and then what we need to add in there as a value. Okay, so the next concept that we're going to have a look at is what's called cyclic redundancy check. So cyclic redundancy check, it's a little bit how we would take a value of 32 and we'll add another value onto it, and then what we want to do is to make it divisible by, say, 9. So 9 into 32 goes 320 goes 35, remainder 4. So the value we will transmit is 324, so that it should be divisible by 9 at the other end. The other end would ignore that value and take this value as the data. So it's really all about adding a value on to our bit values to make it divisible by a certain number. As long as both sides know what the number is, then they should be able to do the calculation. And because we use modulo 2, it becomes fairly simple to actually create both the remainder that needs to be added and also to be able to create the division that's required. Okay, so a common one that we actually use is this one here. x to the 16 plus x to the 12 plus x to the 5 plus 1. So what we do is we take our message data and then we add on some extra bits, and then we do our divide and find out what the remainder is. We then add the remainder onto the message bits, and then at the other end we will then do a divide. If the result is 0, then everything is okay and there hasn't been probably any errors in the value. So this value here can detect single, double, triple errors and so on. It's fairly robust and well defined in the industry. Okay, so here's an example here. So as we've seen before, what we would get is our message. Okay, there's our message value there, and there's the representation. And then we have our polynomial, which will do the dividing on either side. And then what we do is we add on 3 digits, because we have 4 digits here. We're going to add on 3 digits onto the end of our value. It's one less than the number of bits there, and then we'll do our divide. Okay, so there's our value there, and there's our message plus the extra bits, and we go through the divide again, and we end up with a resulting value of 001. So 001 is going to be added on to our transmitted value here. So we can see here the last 3 bits here have been added. So we'll just try this one out, just to show how it works. Okay, so there we are here. So we're going to add on these extra 3 bits on the end, because we've got 4 bits in our divisor. And then we divide this by this with our modulo to division, and hopefully we'll end up with a value of 01. So that's the value that's actually sent. Okay, so at the other end, hopefully when we do our dividing, then we'll end up with a result of 0 to identify there's been no errors. Okay, so that gives us that. Okay, then at the receiver, we take the value we've just calculated, we take our divide, and then we go through, and then hopefully if there's a value of 0, then it means there has been no errors in the transmission. So again, we'll have a look at this one, just to see if everything is okay. Okay, so we're taking the divide there. Well, that's our dividing value there. And when we divide by it, go through, we end up with a value of 0. Okay, so this is a CRC, and there's lots of different types of CRC that we can get. As long as the transmitter and the receiver know what the CRC polynomial is, then everything will be fine. Another method that we can use is what's called longitudinal and vertical redundancy check. So with this, we end up that, so this is our normal parity that we add to our values. So this is the ASCII binary value for a capital F, and we normally have a parity bit. So we can see there 1, 2, 3. So we're going for odd parity here. We add the value to make the number of ones odd. And so this works okay, but obviously it's not very robust. What we do is that we add an extra block onto the end, which is our longitudinal. So we take each of the bits, say the least significant bits in this case, and again we're going for even parity in this case for our LRC, and we add on a bit there. So the advantage with this one is that we can have a couple of errors. Say we have a couple of errors here, so our parity looks okay when we check it vertically, but then when we check it horizontally, then it will be actually incorrect. So this is much more robust than our normal method of just adding a basic parity bit into our code. Okay, so in this case we should be able to take our example, Freddy. So there's Fred, there's the binary values here. And then what we've got is the parity added here. And then we've also got the longitudinal check, which will check across the bits inside the message that we actually send. Okay, so we can send this LRC as the very last value that we have. In this case, it's hexadecimal 28. 28. Okay, 28 is a 2 and an 8. And then that's then sent, and we can do our checking of it. And now let's look at a code that is able to not only detect errors but then correct them. And that's known as one of the codes is known as a Hamming code. So with Hamming code, what we have is that we have the number of bits in the data symbol that we sent, and then the addition of a number of Hamming bits that are required to be able to create our code. Okay, so in this case, if we have four bits in our data, and then if we tried 2 and 2 here, that wouldn't work. If we tried 3, then that would be 8. And a 4 plus 3 is 7 plus 1 is 8. So that complies with it. So one code that we can have is what's called a 4-3 code, where we have 4 data bits and 3 Hamming bits added. Okay, so we start off with the data that we're going to send, and then in this case we're going to add our Hamming bits. We're going to add 4 Hamming bits here to our 6 that we're going to send, and then we place the Hamming bits at positions 1, 2, 4 and 8. Okay, so then what we do is that we find out the total the positions of all the ones in here. So we have a bit at 1 at position 9, we have a 1 at position 7 and at position 3. We then take the XOR of those values that we've created, and we end up with a Hamming code of 1101. So we can now distribute our Hamming bits across here to positions 8, 4, 2 and 1. So they become there, there, there and also there. Okay, so this becomes our Hamming code. So our data is at these positions, and our Hamming bits are here, here, here and here. Okay, so at the other end, we take our Hamming bits out. Okay, there's the code for the Hamming, and then we take the bit positions 9, 7 and 3. Okay, and then we exclusive OR them all together, and we end up with a value of 0. A value of 0 means that we have no error. But let's say now that we have an error in bit position 5, and that becomes a 1. So we now see that appears there. When we create our exclusive OR, then we actually get a value which is non-zero, and we can identify that bit position 5 needs to be corrected. Okay, so if we want to show that mathematically, so here's an example. So our first parity bit checks position 1, 2 and 4 of the data, and so on. So the receiver then becomes, we add in the parity for it. To represent mathematically, what we do is that we would lay out our data such as this. So there's our first bit, second bit, our fourth bit, and then our 8th bit there with the data in between. Okay, so this is then represented in this form for us to be able to multiply by our Hamming matrix. And basically what happens here is that the first row checks for the first parity, the second row for the second, and then so on. So we take this matrix and then we multiply it by our data plus parity, and then that will give us the data that we actually send. Okay, so what we do is that when we receive it, we take our what's called our Hamming matrix and our value, and then we end up with our syndrome matrix, which actually gives us a value which will be related to whether there's an error or not. Okay, so if we take an example, so this is an example here where we have some data 1010. Okay, so we can calculate the first parity bit. Okay, so that's going to be checking for the first, second and fourth digit, so it becomes a 1. The second parity bit checks for the first, third and fourth, so in this case the first, third and fourth, so it becomes 0. And the third parity bit checks for second, third and fourth, second, third and fourth, so it becomes a 1. So this becomes our matrix here. There's the positions of our data, and then there's the positions of our parity bits. So when we check, we multiply this by our data. If we do the calculations, then we end up with a value of 0. If we now have an error in there, and then this one is an error, that becomes a 1 there. And when we do our calculations, we end up having a certain value in our syndrome matrix. So what we'll do is we'll have a look at that in action. So if we just go back to our coding here, and you should be able to find all your examples here, and we'll just have a look at our Hamming for our Hamming code here. Okay, so this will do the calculation actually for us. So there's the matrices that we have, and then what we should find is that when we put in our value, it will give us the result there with our Hamming bits, and then when we do our calculation we end up with 0. But in this case what we've done is to be able to add in an error at each of the different positions, and then when we do the calculation we see there we get a value which is non-zero in terms of the error position. So in this case the Hamming code is allowing us to be able to find out the position of the error that we would map to, and then to be able to correct that. Okay, so that's been a presentation on some basic error coding.